Hello everyone, today I'm going to talk about the power of resonance. We always see or hear about the following scenarios in movies. Soprano can break glass goblets. On a stage with powerful high pitch, the glass on guest tables could break. But is it really true that this can be accomplished simply by human voices? Today I want to talk about the conditions to make it happen theoretically. Waves have energy, and the louder the sound is, the more energy there is. But only by voices loud enough. This is still impossible. There are experiments asking random people to try using their voices to break the glasses, but they all failed in the end. This is because, except the amplitude of waves, which stand for volume, there are other conditions affecting. One of them is the frequency. By frequency, it is not the faster the better, but instead how it can resonate with the glass we're testing on. Every object has its unique frequency, which depends on the property, size, shape, and etc. To enable resonance, we need to know the special frequency of the glass first. To solve for the frequency we want, we start from the wave function. And to solve for wave function, we need angular velocity. And everything starts from energy. Let's simplify a goblet first. In the real life, a goblet can be really complex, but here we have a goblet of height of h, thickness of alpha, and radius of r. In class, we have talked about the energy equation. Total energy equals to kinetic energy plus potential energy, and can be expressed in constant A times x prime squared plus b times x squared. Based on this, we can do a derivative of this energy and get E primes equals to 2a times x double prime x prime plus 2b x prime times x, which is also equals to 0. And from there, we can get a simplified equation, which is x double prime plus b over a times x is equals to 0. And from this equation, we are able to solve for x, which is equals to cosine square root of b over a times t and equals to cosine of omega t, and omega squared will be equals to b over a, and here is our angular velocity. Here it is a top view of a goblet with testing on, and it has a tangent direction, and it also has a normal direction. On the normal direction, we can express the velocity as this wave function. And for tangent direction, we can express the velocity as this following function. We know the total energy equals to kinetic energy plus potential energy, and with all the above conditions we solve for, we are able to get kinetic energy. However, we still need the potential energy. I did a few research on potential energy, which I am not able to solve by myself so far, and found a really nice data on this website. And here potential energy is expressed in an equation which is related to the Young's modulus. Now the both condition to solve for the energy is known, and going back we are able to solve for the angular velocity just as we talked about, and knowing the angular velocity we'll be able to solve for the frequency, and this special frequency for the goblet is looking like this. To make it clear, y here is the Young's modulus, rho is the density of the goblet, alpha is the thickness of the goblet, r is the radius, and h is the height. Now as we have the frequency expression, we're able to do a real-life example of a cup of 10 centimeters height, 3 centimeters radius, and thickness of 1 millimeter, and Young's modulus of the glass. Also, the density of the glass is stated according to this website. By plugging in the data that we have, we're able to solve for a frequency of about 20,000 Hertz. We know that the frequency of people talking has about 100 to 200 Hertz, and the frequency of the professional singer can reach to 105,000 Hertz. However, this is for a cup like this, human voice alone cannot break it. But don't give up, as now we have the expression for the frequency. We can choose another goblet. and there are errors involved in these experiments, and also we can use technology. Under the right condition, we are able to use resonance, the power of it, to break the goblet. And that's all of what I want to share today. Thank you.